Okay, so let's take a look at this system here. We've got a linear system with two equations in the variables x and y. So the augmented matrix, let's start this out the same way we did the previous example, is going to look like this. We're going to have the first row is going to be 1, 1, 4. The second row is going to be 3, 3, and 6. Okay, so that's our augmented matrix. And now I'm going to go out of my way to make sure that we actually see an example of a row operation of the second type, because we haven't actually seen one yet. So this, you might not necessarily choose to do this step normally, but I'm going to pick it now just so that we can say we've seen one of each type. So I'm going to take row 2 and I'm going to replace it with 1/3 row 2. So I'm multiplying row 2 by a non-zero constant, and that non-zero constant happens to be 1/3. So okay, so what's that going to accomplish? Well, the first row is going to stay the same. We're going to end up with 1, 1, 4 still. That's not going to change. And the second row is going to change, though. If you multiply each of those entries in the second row by 1/3, you're going to get 1, 1, and 2. Okay, so now what I'm going to do is I'm going to take row 2 and I'm going to subtract row 1 from it. So I'm going to take row 2 and replace it with row 2 minus row 1. Really, I'm just doing the same thing I did last example. I'm just trying to introduce ones and zeros over here to simplify things so that the solution, whatever it is more apparent. Okay, so well, what's going to happen if I do that? Well, I'm going to have 1, 1, 4, 0, 0, negative 2. That's what I get if I do the subtraction. So, okay, what we're seeing here now is something that has a name. At least I don't know if the book uses this, might not use this terminology, but I like to use it. I find it's helpful to have something to call these. These rows that look like this, so I just want to highlight it a bit with a bubble. It follows a certain form, right? You'll notice that all of the entries over here, the coefficients, are all equal to 0, and the constant term is non-zero. That's the hallmark of a contradictory row. So I'll do it in green here, why not? Okay, this is called a contradictory row. Or you'll hear me use this terminology. So let's define it officially. So, and why is it called a contradictory row? Well, let's translate it into an equation. Right? The coefficients, the zeros to the left of the vertical line, the zeros over here, those are coefficients of the variables x and y. So really, what it represents is, I'll stick with green since that's what I wrote down here. We've got 0 times x plus 0 times y is equal to, and then the constant term is negative 2. So look at that equation, and you decide if you think that there's any values that you can assign to x and y that are going to make that equation be satisfied. And give yourself a few seconds to think about it, and in fact pause this video if you want, but what you're going to find is that it's never satisfied. No matter what you assign to the variables x and y, the left-hand side is going to always be 0 because they're both being multiplied by 0. Both of those variables are being multiplied by 0. So the left-hand side is always going to be 0, and if the right-hand side is negative 2, well, that equation can never be satisfied. So let's just finish this off and say is never satisfied. Okay, so if one of the equations in your linear system can never be satisfied, well, then it's certainly going to be impossible to find a way to satisfy all the linear equations at once. So whenever you run into this situation, you can immediately stop and with 100% confidence say that the system has no solution. So the system has no solution. That's all I'm going to say. And since that's our final answer here, we still solved the system. We didn't find any solutions, but we should, if we did, there'd be something wrong, right? Because there aren't any solutions. So if someone asks you to solve a linear system and you find out that there's no solutions at all, then just tell them there's no solutions, and that counts as solving the system. Okay, so that's what it means to solve that system. So here's an example where there are no solutions.